Hey, hello, and welcome to the show. It's me, JP. It's time for JP's product pick of the week. Here we are. Again, it's a Tuesday. Thanks for stopping by. I will start off by saying head on over to these two URLs, or that one QR code, but these two URLs. Those are the two product picks we have today. Today is a dual pick. They're very similar items, just a couple different flavors of a similar item depending on your needs. And if you head there, you should be getting a 50% off deal on these picks today. Yeah, wow, what a savings. I'm checking them out right now myself. Excellent pricing on these. So head over there. You can watch this show from inside the product pages. So when you go there, just scroll down a little bit and you'll see a little video playing right there. It's this show right here that you're already watching. So head on over there and check it out. Thank you for stopping by our Discord. If you're somewhere else and you're wondering where the chat is, jump on over to our Discord. It's at adafruit.it/Discord, and you can look for the live broadcast chat channel. That's this thing that you see going on right here. Also, hello Dave Odessa. I see you over there in the YouTube chat. If you are somewhere else like Twitch or Facebook and you're wondering where all the chatting is, that's where you want to be, is our Discord. So jump on over there if you can. And without further ado, I'm going to have Lady Ada jump back a little bit in time and talk to us briefly about today's product picks. So take it away, Lady Ada.
We got two updates. We've got the ADS1x15 and the ADS1x15. Two I2C analog digital converters are very popular. But we've stomach QTified them because we love to add plug-and-play support to all of our breakout boards. So we're kind of going backwards in time, and now we're getting to the older boards. So these are 12 and 16-bit ADCs. They work over I2C. There's tons of support for them. There's Arduino support, CircuitPython, MicroPython, Everyday Python, Rust, whatever. It's like these are kind of ancient, and so they're well documented and well supported. The 16-bit's a little bit more expensive. 12-bit is going to be good enough for most uses. It's actually kind of it's not common to see I2C ADCs. Most ADCs are SPI. And so, these are very handy for when you just have to add some high-quality analog inputs, or if you have a board, propeller chip, for example, or a Raspberry Pi that doesn't have an ADC, plug it in. And so now what we've updated is it comes in the STEMMA QT format, which means it's got these JST-SH connectors. You can use cables to plug and play them with our Feathers, with Raspberry Pi, so no soldering required. Of course, if you want to connect to the output pins, you may want to solder to them. But at least for the entry-level wiring and testing, no soldering is required. And you can have up to 4 of these, I think, on one I2C bus just by noodling with the address pin. I think tying it to ground or tying it to SCL will let you choose multiple addresses as well. So, very easy, very reliable way of adding multiple 12 or 16-bit analog inputs.
Yes, indeed. That is the product pick of the week. That's it. Look, there it is right there. It's actually 2 of them. I only have this one right here, but let me talk about these. So that's my product pick of the week this week. It is the ADS1x15 ADC. This is the 16-bit one. This is the 1115. We also have the 1015, which is a 12-bit. And we're doing both of those today at a discount. So head on over to their product pages and get them for half off. This is a really terrific analog to digital converter. That's what an ADC is. So some microcontroller boards will have a few ADC pins, and they're often something like 10-bit resolution, so not super high resolution. Some boards you'll work with might have no ADC pins, so this is the type of thing you want to add. This will give you up to 4 channels of high quality, high resolution analog to digital conversion, perfect for knobs and sliders and soft potentiometers or other analog sensor reading needs. This can be used in a differential mode where you have 2 pairs of channels tied to each other, and that'll allow you to get a higher precision and also go into negative voltages. But I'm going to show you a demo where I'm using this to add really nice high resolution. I'm just using 2 potentiometers, 2 10K potentiometers, to give myself really nice high resolution that I can use for tuning an oscillator or a couple of oscillators. So I'm going to have a couple of audio pitches And you want quite a bit of resolution to get those pitches to be exactly where you want them to be. So let me show you that demo here. I'm gonna jump to my overhead, and I'll need to refocus that a little bit, talk about what I've got here. Okay, so here's my speaker. I've got a little extra microphone over here, so hopefully you'll be able to hear this a little bit better. There we go. That's pretty good. So one, let me jump a face of mine back in here. One really nice thing about these boards is that we have I2C connectivity to your microcontroller, and you can do it without any soldering if you use these STEMMA QT/quick connectors. So you can see this one here has a nice little STEMMA QT connector, and I'm plugging that right into a Metro M7 board. I also have an amplifier and some extra wiring here that's not part of this project. And the amplifier has a nice little 4 ohm speaker sitting over here, 3 watts. I have a couple of 10K pots, and I put some neat old Bakelite knobs on them. So what's going to happen here is that I'm going to be reading those knobs and then turning those values into the frequencies or pitches that we hear on a pair of sawtooth waveform oscillators. So let me turn up this speaker here. Let me know if there's any issues with the audio mix there. Okay, so here I wanted to tune a nice interval, and I can really fine-tune that. Thanks to that high resolution of those ADCs. So let me turn that back down, and I'll show you in code what that looks like. You can see, first of all, just watch the, I'm going to turn down the audio a little bit. Just watch the values there. This is the raw values that I'm reading on one of those knobs. So you can see I've got really high precision, high resolution. Okay, so I'm taking those values, which I'm reading. In this case, it's, I believe, 15-bit resolution because I'm using these in single-end mode. You get the 16-bit resolution if you use the differential mode. I think I have that right. And we have a really nice, something like 60-page data sheet for these chips that I'll show you a link to. But if we take a look at the code here, the main things that I'm doing are importing this ADS1x15, and then I'm particularly grabbing the 16-bit one in this case, so then I, from that, grab ADS1115. And then I'm also bringing in the analog in support, so that's what allows me to use up to 4 of those pins as analog inputs. I'm setting that up on my I2C bus, and as Lady Ada mentioned, a lot of times these ADC boards are only SPI, so this one's really nice and convenient because it works over I2C, easy to plug into other microcontrollers. Then I'm also setting up my synthesizer stuff, my amplifier output, but really the key thing that you can see at the bottom of the code here is I have 2 notes that I'm playing, and the frequency of one of them is my value I'm reading off of. I happen to be using channels 2 and 3. There's 0, 1, 2, and 3. So channel 2 value and channel 3 value. That's how easy it is to read those off of the ADC here. And then I'm just making the range a little smaller as far as the pitch range that we can hear just by dividing that. So I'm dividing that by 48. And I'm also preventing any noise fluctuations that might drop that slightly negative. Sometimes the value will go down to like -1, and that'll freak out the frequency of the synthesizer, which doesn't like anything below 0. So that's what this little max here of whatever that value is and 0. So that'll make that the smallest number that it can go. So There's our little 2-note drone synth there. If you take a look at the product page here, I'm going to jump over to this view of the world here. You can see, so here's the 16-bit one. You may want to spend less and get the 12-bit one if your needs don't require you to have that extra resolution, so you can save some money. As Lady Ada mentioned, you can chain these together on the I2C bus, up to 4 of them, by adjusting their addresses. So if you needed a whole bunch of 12-bit ADCs, you need 16 knobs on a project, this would be a nice way to do that with pretty high precision, or jump over to the 16-bit one and get even higher resolution. You can check out the Learn Guide. Actually, Liz did a Learn Guide that covers both of these boards. They're essentially identical, other than some small changes in the library usage. And this will show you the pinouts for the boards. You can see across the top there, in fact, let me jump to this photo here for a moment. You can see across the top there we've got the positive A, and then on the far right the negative A. So those are the analog voltage references. Those are, in this case, I'm using this over I2C, so it's a 3.3 volt reference, but you can go up to 5 volts, down to 2 volts with this. And then those middle pins, A0, 1, 2, and 3, are the 4 channels that you can read either in single-ended mode or pairs of the 2 of them in your differential mode. And then down at the bottom we have the I2C pins broken out. If you don't want to use the stemma QT connectors, you can use those, solder some headers on, as well as the address pin that you can use to set different addresses on these. So checking out the guide again, you can see here we have all of the usual facts and info there about your pins and how to use them, as well as how to set the different addresses for these to chain a bunch of them together. Section on assembly and wiring. Your signal connections here will show you what to wire up depending on what you're reading. And this is an update. It's actually a 2nd level update on a board that we've had for quite a while. It got a form factor change and added the stemma QT, and then the most recent version added the really nice silk screens using Penguin. And then you can see here there are some examples of some CircuitPython code, some Arduino code, and some Blinka code if you want to use this on something like a Raspberry Pi, which is perfect because you don't have any analog pins on a Raspberry Pi, unless something's changed. But I'm pretty sure you have no analog pins, so if you want to do something as simple as read a knob, you can grab one of these and use it over I2C with your Raspberry Pi and the Blinka library. So was just noticing over in the Discord, Tyeth says these are the bee's knees. Got lots from another place many moons ago, but the I2C plug and play is always better. Yeah, super convenient there. Keith over in the YouTube said it sounds like an air raid siren. It absolutely does. I was actually goofing around with hooking these together with I just had like a rubber band around them, and I pitched them and then was trying to move them together, and it sounded, well, it sounded pretty alarm-like. Here you go. One other thing you can do with the higher resolution is actually get really darn close to tuning it so well that you don't hear too many phase offset beats. I haven't gotten it perfect, and it may be that I need to shut the range even tighter as to what voltages or frequencies I'm sending to this, but you can hear, if I want to tune these in unison to the same pitch, this resolution allows me to get really close. So here we go. So you hear a little bit of phasing, but otherwise those are in pretty tight pitch. You can also, let me jump back over to the code. If we use a sine wave, you can really, there's nowhere to hide with a sine wave because we don't have all of those harmonics. So if I come into the code here and just change which waveform I'm specifying when I instantiate this synth object, now it's going to be You can hear it cancels itself out in the phase because the phase isn't perfect, but it's pretty close, which is pretty impressive for this simple setup and just a little bit of synth.io code. Sine wave is quiet too because it doesn't have the benefit of harmonics. I can raise that volume. Pretty close. Pretty close. All right, turn that down. So, I'm going to turn this mic off here. I think that covers it. So you can check these out. Head on over to that URL that you see right there, either of those. And there's both the 12-bit and the 16-bit versions of these. Like I said, you can use these in single end or in differential mode, depending on what you're trying to measure and the precision that you require. But really nice, easy way to add some knobs, faders, soft potentiometers, maybe some of those stretchy fabrics. Do those work that way? I think they do. You've got all kinds of analog sensors that you might want to use in your projects, and this is a really nice way to work with them pretty easily, 4 of them at a time, up to 16 if you batch these together over I²C. Let's see, anything else I've missed? I mentioned, actually, if you head to the product page, you can click on a link that'll take you to the Learn Guide, and if you go down to the downloads, you'll see the data sheet here. There's a data sheet for each of the 2 from Texas Instruments. And this is a hefty one. Like I said, it's something like 60 pages long, but you will find it. If there's info you need, you'll find it in there. One thing I didn't mention, I think, is that you can use gain up to 16x gain. Maybe I mentioned this, but depending on the type of signal that you're trying to read, you can gain that up or leave that at a default of 1 gain. Let's see, anything else? This has internal low drift voltage reference. It has an internal oscillator on it, so really set up nicely. I believe we're using 128 samples per second on the reads, on the analog reads. You can, and that's, I think, baked into our libraries, but if you wanted to, it is possible to go up to, I think, 860 samples per second on these, so really fine-grained, high resolution. All right, I think that will do it. So go grab yourself some. That is my product pick of the week this week. It is the ADS1x15 16-bit and 12-bit ADC Breakouts with Stemma QT. Thanks everyone for joining me for Adafruit Industries. I'm John Park, and this has been JP's product pick of the week. Bye-bye. Don't hurt anyone, Lars.